Hey everyone, welcome to a complete breakdown of Python's core concepts. Whether you're just getting your feet wet or looking to lock down your fundamentals, we're going to dive straight into the syntax, data types, and core mechanics that make this language tick. Let's get into it. So, why is Python practically everywhere you look? First off, it's readable by design. The syntax is super clean, almost like plain English, which completely cuts down on the cognitive load when you're writing or reviewing code. It's also an interpreted, dynamically typed language. That means there's no tedious compilation step. The interpreter handles everything at runtime, and you don't have to explicitly declare your variable types up front. From quick scripts and automation to heavy lifting in data science, web dev, and AI, it's a massive ecosystem powered by a huge stdlib. Alright, let's talk about the absolute golden rule of Python. Indentation is everything. Forget about curly braces. Python uses whitespace to define its code blocks. Now, technically, the interpreter doesn't care if you use one space, four spaces, or a tab, as long as you stay completely consistent throughout the block. But look, PEP8 mandates four spaces, so just stick to that universal standard to avoid throwing an indentation error. If you look at the snippet here, you can see how the statements inside our if-else blocks are neatly aligned, while the final print statement sits flush to the left, running completely outside the conditional logic. Moving on to variables. Like I mentioned earlier, Python is dynamically typed. You don't need any boilerplate code to typecast your variables. The interpreter just infers the data type at runtime based on the value you assign. And because variables are just references to objects in memory, you can rebind a variable to an entirely different data type later on without the compiler screaming at you. When it comes to numbers, we have integers and floats. One awesome feature here is that Python integers have arbitrary precision. They'll scale up and grow as large as your system memory allows. Floats, on the other hand, follow the standard IEEE 754 spec. Check out the operators. We've got standard math, but notice how a single forward slash gives you true division, returning a float, while a double slash handles floor division, dropping the remainder. If you just want that remainder, use the modulus operator. Oh, and for exponentiation, it's a double asterisk. Just keep in mind, if you mix an int and a float in an expression, Python automatically promotes the result to a float to avoid losing precision. Strings in Python are completely immutable. Once you instantiate a string in memory, you cannot mutate it in place. Trying to swap out a character directly via its index will just crash your program with a type error. Instead, you have to spin up a brand new string object. Speaking of indexing, Python uses a zero-based system. Positive indices read left to right, but you can also pass negative integers to read backward from the right, where -1 gives you the very last character. Slicing is also incredibly powerful. Passing 0:5 grabs a chunk of the string, and using the $:1 trick is a quick idiomatic way to reverse the entire string. Alright, so let's talk about case transformation in Python. These are 4 string methods you're going to use constantly, so it's worth getting really comfortable with them. First up is .upper. Dead simple, it just shouts everything. Every character in your string gets converted to uppercase. Then there's .lower, which does the opposite. Everything goes lowercase. Super handy when you're normalizing user input, like comparing emails or usernames without worrying about how someone typed it. Now, .capitalize is a little more nuanced. It only uppercases the very first character of the whole string, and it actually lowercases everything else. So if you've got some weirdly cased string like Jack Sparrow, .capitalize will clean that up to just Jack Sparrow. And finally, .title gives you title case. So the first letter of every single word gets capitalized. Think book titles, headings, that kind of thing. One thing to burn into your brain. None of these methods mutate the original string. They all return a brand new string. That's because strings in Python are immutable. You can't change them in place. So always make sure you're capturing that return value. Okay, next up we've got 2 methods that are absolute workhorses for text processing, .find and .replace. Let's start with .find. You call it on a string, pass in the substring you're looking for, and it hands you back the index, the position, where that substring starts. And remember, Python uses zero-based indexing, so the first character is at position 0, not 1. So if you've got a long message string and you call .find with welcome, it'll tell you exactly where that word kicks off. Now here's the thing. If the substring isn't in there at all, .find doesn't blow up and throw an error. It just quietly returns -1. That makes it really safe to use inside an if statement to check whether something exists before you act on it. Now .replace is where things get fun. You pass it two arguments: the substring you want to swap out and what you want to replace it with. It scans the whole string and makes the substitution. But here's the gotcha. It's case sensitive. So in our example, apples with a lowercase a gets replaced, but apples with a capital A, totally untouched. And just like all the other string methods we've seen, .replace doesn't modify the original string, it returns a new one. So always assign it to a variable, otherwise that transform string just disappears into the void. Now let's talk about the bread and butter of string manipulation, split and join. The .split method takes a string and breaks it down into a list based on a delimiter you pass in, like splitting a comma. Separated string into individual elements. .join does the exact opposite. It takes a list or any iterable of strings and glues them back together into a single string, using whatever string you call it on as the separator. It's way more efficient than concatenating strings in a loop. If you're still formatting strings using old-school % formatting or the .format method, it's time to upgrade to f-strings. Introduced back in Python 3.6, formatted string literals are the modern standard. You just prefix the string with an f and drop your variables or expressions right into curly braces. The interpreter evaluates them on the fly at runtime. It's cleaner, highly readable, and under the hood, it's significantly faster than the older approaches. Python gives us 4 core built-in collection types, and picking the right tool for the job makes a massive difference in both performance and readability. First, lists are your standard, ordered, mutable sequences, the ultimate general-purpose container. If you have data that shouldn't change, use a tuple. They're immutable, ordered, and slightly faster than lists. Sets are awesome when you need to enforce unique elements and get rid of duplicates automatically. Plus, they give you lightning-fast lookup times and support classic mathematical operations like unions and intersections. Finally, we have dictionaries for key-value pairs. They offer fast, average O(1) lookup times, and ever since Python 3.7, they officially preserve insertion order, making them essential for handling structured data layouts. Wrapping things up with control flow, the if-else chain executes conditions from top to bottom. The moment the interpreter hits a condition that evaluates to true, it fires off that specific block and skips the rest of the chain entirely. Also, if you want to keep your code concise, Python supports a ternary form. It lets you evaluate a condition and assign a value inline on a single line, which is great for keeping simple conditional assignments clean and boilerplate free. Alright, let's look at loops in Python. When you know exactly how many times you need to iterate over a sequence or a range, a for loop is your go-to. It's deterministic and handles the sequence under the hood. On the flip side, if you're dealing with open-ended or event-driven logic, where you just need to run as long as a certain condition stays true, you drop in a while loop. Just make sure your while condition eventually hits false, or you're going to spin up an infinite loop and lock up your REPL. Regardless of which loop you use, you can always drop in a break statement to bail out early, or a continue statement to skip the rest of the current block and jump straight to the next iteration. Also, a couple of quick pro tips. Use the range function to generate large sequences on demand without destroying your memory footprint. And if you ever need both the index and the item at the same time, wrap your iterable in enumerate. It's way more idiomatic than keeping track of a counter variable manually. When you want to dry up your code and stop repeating yourself, you wrap your logic into functions using the def keyword. They accept parameters, execute your block, and optionally pass data back out using a return statement. If you don't explicitly declare a return value, Python just implicitly hands back none. Another sweet feature is default parameters. As you can see in the greet example, setting a fallback name means your function runs seamlessly even if the caller doesn't pass an argument, but it still gives them the flexibility to override it when they need to. Sometimes you have no idea how many arguments a user is going to pass into your function, and that's where star args and double star quargs come to the rescue. A single asterisk before a parameter name packs an arbitrary amount of positional arguments into a single tuple. The double asterisk packs variable keyword arguments into a standard dictionary. Inside the function, you can pass them dynamically, loop through the items, or pass them down the chain to another module. It's super common when you're writing wrappers or working with flexible APEs. Variable scope in Python works like a system of one-way mirrors. If you spin up a variable inside a function, it's local to that namespace. The code inside the function can look outward to see global variables, but the outer scope is completely blind to what's happening inside. If you try to call local_var from outside the function's block, the interpreter will have no clue what you're talking about and immediately throw a name error. So how does Python actually resolve names when you call a variable? It follows the LEGB rule, checking 4 specific namespaces in a strict order. First, it looks at the local scope inside the current function. If it's not there, it checks the enclosing scope of any nested or wrapper functions. Next, it looks at the global scope, which is your module level. Finally, it scans the built-in scope, things like the standard print function or exceptions. If it strikes out at all 4 levels, it gives up and raises a name error. Let's move on to object-oriented programming. In Python, a class acts as your blueprint, defining the attributes and behaviors for an object. When you instantiate that class, you create a concrete instance with its own state in memory. To initialize your data, you use the dunder init method, which serves as the constructor. Notice how every instance method requires self as its very first parameter. Self is just a reference pointing to the specific instance calling the method, letting you read or modify its own internal attributes. Inheritance is all about code reuse. It lets a child class automatically adopt all the attributes and methods of a parent class without writing any boilerplate code from scratch. Take a look at this snippet. The car class inherits directly from vehicle. Because of that relationship, an instance of car can seamlessly call the parent's start_engine method, but it can also extend that behavior with its own specialized methods like drive. Polymorphism lets different classes implement the exact same method interface, but execute completely different logic under the hood. In our example, both the dog and puppy classes expose a speak method, but dog returns a woof while puppy overrides it with a yip. This means you can iterate through a collection of different object types and trigger the same method name cleanly without writing a bunch of messy conditional checks to figure out what type of object you're dealing with. Exception handling acts as your application's safety net. Real-world code fails, whether it's an end user typing in bad data or your code trying to divide by 0. Instead of letting the program ungracefully crash and burn, you wrap risky operations in a try-except block. You can catch explicit, predictable errors like value error or zero division error to handle them safely, and then provide a fallback catch-all for any unexpected generic exceptions. As your codebase grows, you need to think about how you're organizing your files. In Python architecture, individual .py files are called modules. When you group related modules into a directory, that folder becomes a package, as long as it contains a dunder init file to signal to the interpreter that it's importable. Then you usually have a main.py script sitting at the root of your project, which serves as your clean entry point to boot up the whole application. To wrap everything up, let's talk about the import system, which keeps your code modular and DIY. Python comes out of the box with an incredible standard library. You've got math for mathematical constants, OS and sys for interacting with the host system and interpreter, datetime for timestamps, and JSON for passing API payloads. You can pull these in using different import styles depending on whether you want to import the entire namespace or just pluck out a specific function to keep your workspace clean.